Hi guys, 2, 5, zeros of polynomial functions. This is a big section and we have several theorems between lesson 4 and lesson 5, and you need to make sure that you're keeping those straight. I'm going to recommend that you make some note cards and that you put the name of the theorem on the front and the theorem itself on the back. You can also do that by folding your paper like a hot dog style vertically in the middle and putting the name of the theorem on one side and then what the theorem is on the other side. Okay, if you have questions about that, let me know, and I can help you get something organized there. But the first thing, use the rational zero theorem to find possible rational zeros. So just want to talk about this real quick. I'm not doing examples 1 and 2. I'm expecting that you go and do those before you go on with the video talking about objective 2. Okay, but the rational zero theorem, it finds possible rational zeros. So let's break this down for a second. A zero is an x-intercept. A rational x-intercept means that it's an x-intercept that could be written as a fraction, like 5/3, or -1/2, or 7. Okay? So what the rational zero theorem does not find is any irrational zeros, like 3 plus the square root of 2. Okay, the rational zero theorem doesn't do that. That would need an irrational zero theorem, and to my knowledge, there isn't one of those. And then also, backing it up one more step, to find the possible ones. What the rational zero theorem does for us is it narrows the possibility from any number from -infinity to +infinity as being a possible rational zero. It narrows it to a much smaller set of values. Okay, and we're going to go through an example of the where we use rational zero theorem in doing objective 2, which starts with example 3. Okay, so if you haven't gone to the book to work through checkpoints 1 and 2 in this section, go do that first and then come back to the video. Okay, if you're still with me, you've done examples 1 and 2 and checkpoints 1 and 2 already. 2.5, objective 2, find zeros of a polynomial function. In section 4, you were given a similar problem, except they gave you this function, f of x equals, and they already told you one of the zeros. Okay, they said the first zero is, or one of the zeros is, and they gave you a value. And then you went through the process of finding the other zeros if you know that value. All this does is add one step to that. You now have to find the first zero yourself, okay? But then the rest of the process is going to be exactly the same. Make sure you're taking notes because we have some theorems I'm going to be throwing at you here. So the first one, the rational zero theorem. From checkpoints 1 and 2, you know that that depends on the factors of p, which is your constant number. We do separate any positive or negative from that. We don't look at this. We only look at the 6. Okay, the q are the factors of your leading coefficient. In this case, it's just 1. Okay, so the factors of 1 are just 1, and the factors of 6 are 1, 2, 3, and 6. Okay. The rational zero theorem says any rational zeros will happen at a plus minus p over q combination. Any other ones are out of the question. They will not happen anywhere else. Okay, so what we're going to do is we're going to look at these plus minus p over q's. The p's all come from the factors of p, the constant. The q's come from the factors of q. You have to pair every p with every q. That's easy here because we only have one factor for q, but make sure if you have multiple factors for q, that you go back and you pair every p with every q. Okay, so here I just did 1 over 1 and 2 over 1 and 3 over 1 and 6 over 1. And it could be the positive or negative version of any of those 4 numbers. You can simplify this to be plus minus 1, plus minus 2, plus minus 3, plus minus 6. Okay? All right, so we have 8 different possibilities that we need to test to find one of them that's a 0. Once you find one of them that's a 0, you can stop testing and you can just go on with that solving process like we did in 2-4. Okay, so I like to go in order and not jump around. So the first thing I'm going to test is positive 1. Okay, so to touch on the things that I've written up here that you just now see, again, this is the rational 0 theorem. It does not apply to irrational roots like square root of 3. It also does not apply to complex roots. Imaginary is what I'm saying there. And you have to test each 0 until you find one that works. You don't have to continue to test all 8. Once you find one, you can roll with that. Okay, so testing this 0, we're going to use the factor theorem that you talked about back in 2-4. Okay, we talked about that. We take the f of x, and these are the coefficients of f of x. It was 1x cubed plus 2x squared minus 5x minus 6. Okay, and we're going to do this synthetic division with a 0 of 1. All right. So we drop the 1, and then we multiply the 0 of 1 by this 1 to get 1. We record it under the 2. And then 2 and 1 give us 3. Multiplying the 1 with the 3, we get 3. It was this 1. It's always multiply the 0 by the number underneath. Okay, bringing these together naturally, we have negative 2. And then negative 2 and negative 6 give us negative 8. This remainder is not 0. Okay, that was the test back in section 4. We tested the 0 and we expected to get a remainder of 0. The factor theorem says if you divide by a 0 and you get a remainder of 0, then this really was a 0, using the word 0 a whole lot. This was a 0 of your function. If you divide and your remainder is not 0, then x equals 1 is not a 0 of f of x. But it is still significant because there was another theorem that you guys have had that you've seen and should have taken notice of, and that's called the remainder theorem. The remainder theorem says, and this is really cool, that the remainder value that you get here is actually the function value of your 0. Okay? So if you do f of 1 up here, if you do f of 1, 1 cubed plus 2 times 1 squared minus 5 times 1 minus 6, you're going to get negative 8. Okay? Our Algebra 2 book called that synthetic substitution. They don't use that terminology here in your Blitzer book, but you could search online for that if you wanted to see another example. But this is called the remainder theorem. The factor theorem demands a remainder of 0. The remainder theorem says whatever your remainder is, that's the value of f of your number. Okay? There's going to be a bonus associated with remainder theorem if you remember to ask me. All right, so we've got to try again because remember we need to find a 0 that works. Test each 0 until you find one that works. So we've got to try again. We're going to try again. This time we're going to go negative 1. We tried positive 1. That didn't work. Let's try negative 1. And we have bring down the 1, multiply negative 1 by 1 and get negative 1. Another 1. A negative 6 with the negative 5 and negative 1. Multiply to get positive 6, and our remainder is 0, and that is a good thing. Okay? Had to pause for a second, so if I repeat myself, I'm sorry about that. But because when we did this division with the negative 1 as our 0, because we got a remainder of 0, that check mark means that x equals negative 1 is a 0 of f of x. So we don't have to continue on with the other 6, for those of you who are groaning because you have 8 things to check. We don't have to continue on with those. We found 1, 0. Okay? And now we're back to the process that we worked on in 2, 4. Okay, so we know x equals -1 is a 0. And we also, remember that depressed polynomial? Okay? X, this 1, 1, -6, those are the coefficients of our depressed polynomial, which I have written right here. 1x squared plus 1x minus 6. Okay? The other thing, remember we need to, or we can think about if x equals -1 is a 0, then x plus 1 is the factor of f of x that is produced, that produces this 0. Okay, so what I'm going to show you is our f of x written in factored form. Okay, so we have x cubed plus 2x squared minus 5x minus 6, and we're setting that equal to 0. And then we can break that up to be x plus 1 and x squared plus x minus 6. Remember that came from the x equals -1 factor and this 1, 1, -6, the coefficients of our depressed polynomial. That just means it's inside of it somewhere and we can't see it. To find the zeros, we will then try to factor this down some more. And we can actually do that to get x plus 3 times x minus 2. Okay? If you could not factor, you would not be off of the hook. You still have to find the 2 zeros that come from this equation or this factor, but you would have to do it with completing the square or quadratic formula, one or the other. Okay, so I really hope we can factor, because quadratic formula and completing the square are way more work than we need if we could have factored to begin with. Okay, so here this is in fully factored form. These are all linear factors, meaning they're all x to the first plus 1, x to the first plus 3, x to the first minus 2. And so -3, coming from the middle factor, -1, and +2 are the 3 zeros for this polynomial. I'm going to check what the next example is. My brain isn't working at the moment. To see if I'm going to cut you off now or if we can do one more. All right, let's go ahead and I'm going to do a new video for this next example.